All right. I think I already have a video of this, but I'll make another one. I can't remember if I did it during a lesson or not, but it doesn't matter. So we're continuing on with our thermodynamic lessons. The last couple of lessons we've done experiments where we've used calorimetry to calculate various delta HX's, molar enthalpies. In our first experiment, we calculated the molar enthalpy for something dissolving, a physical change. In yesterday's experiment, you will have been determining the molar enthalpy for a neutralization reaction. And again, these are just examples, and again, ways in which we can calculate the delta H. And just kind of a little bit of review, the methods that we can use to calculate delta H. And I've got to think back myself. What was the first method I showed you? Oh, using molar enthalpy, right? Right, using molar enthalpy, enthalpy. In other words, using the equation delta H equals N delta HX, all right? That's just the basic definition to calculate that enthalpy, that delta H. And we've been using that one quite a bit. And that's one that you see in all kinds of different forms and different methods. But again, essentially, this gets us something like kilojoules per mole, and this is moles, and then in the end, this is just kilojoules, right? So the enthalpy, remember, is just that total energy that we would get from a reaction. The second way we did this was calorimetry, right? And that was essentially putting together our N delta HX, which is equal to delta H, in with the negative MC delta T. And that's what we've been doing the last two labs, right? So that was the second way, I believe, on our little list that I had you write down last week. The third way was bond energies. And that is essentially adding up the bonds. I'm trying to think what the equation was. Delta H was the sum of the bonds broken, because that's an endothermic process, the sum of the number of the bonds broken. I think I called it D. These are broken. So those are the bond energies there, minus the sum of the number of bonds that are formed or made or formed. We'll go with formed. I don't know exactly how I had that. And that was adding up those bond energies. When you break bonds, it takes energy. It's an endothermic process. When you make bonds, it gives off energy. It's exothermic, and that's why that negative was in there. All right. And that was the last lesson that you did before we went back and did some calorimetry problems. On that list, the next thing that we have is Hess's Law. All right, so we're now at 4. There is a 5 where we are going to be adding up molar enthalpies. Again, it kind of looks like this, but it's a little bit different. It's using heats of formation, and that's what number 5 is. And so that's what we'll be covering over the next 2 or 3 lessons. So, and it looks like this, right? Today, Hess's Law. Tomorrow, another quick lab on Hess's Law. So we're going to do another little calorimetry lab, but it's going to use Hess's Law. I'm going to make that an informal report as well, just because I've got a lot of marking to do these days. And all of these calorimetry labs have the same error analysis over and over again because we're using the same apparatus, right? And then Thursday, I said I was going to give you a work period / review to prepare for Friday's grade 11 review test, all right? Then on Monday of next week, we will finish off this number 5, heats of formation. Then I got a couple of lessons on what is called spontaneity and Gibbs free energy. And then it's looking like a review next Thursday and then a test next Friday on the thermal chemistry unit. All right. So that's the way this week and then the next week is working out. Okay. So let's talk about Hess's Law of additivity of reaction enthalpies. What a great word. You'd think I made up that word, but chemists actually use it. Additivity. What a great thing. It simply means that we can take a group of chemical reactions that are linked in some way. It's not like we just randomly take chemical reactions, but we can take a series of chemical reactions that add up to a final chemical reaction. And if we want to know the enthalpy of that final chemical reaction, we simply have to add up all of the individual enthalpies. Now that's essentially Hess's law right there. You didn't write anything down. All these words blew right past you, and it doesn't make a whole lot of sense at this point, but it really is a simple thing. It's a very straightforward addition of chemical reactions. Let's talk about why we can do such a thing. Now, some rationale first. You can write down, you've already got the title, all right? Another way of writing it is Hess's law, heat of summation. In other words, it has to do with addition. You don't have to write that one down. Don't write it down. So you got the title. Don't even write down all this slide at all. This slide is just one of these explanation type slides, all right? Let me give you a scenario. And the easiest scenario is the experiment we're going to do tomorrow. Let's say that we wanted to study the heat given off when magnesium burns. You've all seen the combustion of magnesium in probably grade 9, 10. Some teacher sticks a piece of magnesium ribbon in the flame and glows bright and all that type of stuff. Super, super hot, right? That flame is one of the hottest flames that we actually encounter in a high school lab. It's got to be about 1,200, 1,500 degrees, right? The only thing that I've seen mark our lab benches is burning magnesium falling on the lab bench. I did it once, anyway. So that's the only thing. So it's super hot. And if we wanted to calculate the heat given off in a combustion reaction like that, and we don't have a big bomb calorimeter that can take something like that heat, and we only have styrofoam cups, we need to do something a little different. Because if you were to take burning magnesium and drop it into some water, that's a super dangerous situation. That actually becomes explosive, all right? You can't put burning magnesium out with water because the superheat of the burning magnesium actually causes the water to decompose into hydrogen and oxygen, and then it quickly recombines and gives its energy back out in an explosive manner, and it literally causes an explosion. So, number one, it's explosively dangerous. Number two, you drop some magnesium in a coffee cup styrofoam calorimeter, and it hits the side, and you melt right through the calorimeter, and it's really a mess. You really just can't do it. So if we wanted to study such a thing, how can we do this? Well, there are many other chemical reactions that we know that magnesium can undergo that are not dangerous. We could take magnesium metal, and we could put it in an acid, and we could have it react with the acid and bubble in a single displacement reaction, make some hydrogen gas, make some magnesium chloride, and that is still a reaction that contains magnesium and starts the process of breaking that magnesium down. If we could come up with other magnesium reactions that we can add together, literally add them up, like we're adding algebraic equations, and those series of equations then can be added to our combustion of magnesium equation, then we can get what that reaction is by adding up the easier equations. There are many chemical reactions that don't occur in aqueous solutions or release too much energy that we cannot do in a coffee cup calorimeter. Usually these reactions can be broken down into a series of simpler reactions or steps that when combined, so when we add them together, have the same initial reactants and final products as the original reaction we want to do. The delta H's for such a reaction can be determined using Hess's law, and now you can write down Hess's law. You don't need to put the heading, I guess, but this is the statement of Hess's law. The delta H for any reaction that can be written in steps equals the sum of the values of the delta H for the individual steps. So it's all about adding them up. As an equation, it looks like this, but this is one of these equations that I never have you actually directly use. When I show you how to solve a Hess's law problem, we never actually write that equation down. This equation is simply a mathematical representation of Hess's law. When we do a problem, we we solve it using a handful of steps that never actually involves writing that equation down. So if you're someone who likes to put a star beside equations that are important, that we use over and over again, like our molar enthalpy and our calorimetry, don't put a star by this one. We don't actually have to memorize that equation. We don't ever use it in that form, because there's an easier way to write down the problem when we get to this. Now the next slide involves a little potential energy diagram. We've seen the potential energy diagrams before. You saw them when you did the lesson on thermochemical equations, how we can represent a chemical reaction in terms of its potential energy and its reaction progress, and how we can have reactants and products, and whether it's exothermic or endothermic. You know, we can then see whether that energy is being given off or energy being added. This next slide talks about how we can then think about Hess's law in terms of a potential energy diagram. And I don't know if I'd write this down, but it's just a way of thinking about why we can do such a thing. And I'll give you another example in a moment. But let's say that we took some methane gas, CH4, and we burnt it, and we ultimately wanted to get the products, which is carbon dioxide gas, and after it cools down, the water would liquefy and you get some condensed liquid, say on the outside of a test tube. Think back to our good old Bunsen burner experiment. Actually, I got piles of labs. I'm marking the grade 11 Bunsen burner experiment. And think about when you first put that cool test tube into the flame, you see a little bit of condensation on the test tube. If you've ever cooked with natural gas, like if you at home have natural gas or propane that you use on your stove, when you first put that pot on there, if it's cool, like if you got frozen veggies in the pot, you know what I'm talking about? You get condensation on the outside, right? You've seen that before? All right. So for that reaction, what you have is methane gas burning with oxygen to produce carbon dioxide and liquid water. And that's exothermic to the point where 890 kilojoules per mole of methane is given off. But in actual fact, that reaction takes place in two steps. Because right after the combustion takes place, the water is actually in the vapor state. It's actually in a gaseous state. And then once the water vapor touches the cold pot, it condenses and becomes a liquid. The delta H for combustion that results in gaseous water is only negative 802 kilojoules. But then the delta H for the change of state from a gas to a liquid, which is also endothermic, is another 88 kilojoules. Whether you think of the reaction as being one step all the way to liquid, or two steps, combustion to the gas and then condensation to the liquid, it doesn't matter. It still results in the same amount of energy. So you can take a chemical reaction, and if you can express it in a series of simpler chemical reactions, the entire delta H for that reaction can be determined by adding up the delta H's for the simpler reactions. That's what Hess's law is. You can actually take a chemical reaction that's complex and hard to study, break it into simpler chemical reactions, add the delta H's up, and get the total delta H. So we're simply adding chemical reactions like they're algebraic expressions to get the overall delta H. Let me give you another example of why we can do this. All right. This is essentially a version of the law of conservation of energy. Let's say that you were stuck on a cliff here. All right. So you're stuck on the cliff, and you ultimately want to get down to the lower level, right? right here, and it's going to take so much energy for you to get down there. And in this case, it's actually gravitational potential energy, e.g. I'm going to turn this into a little physics problem, right? And if you wanted to get down there, then there's many different ways you could get down to that lower level. If there were some steps built in, you could then take a whole bunch of little steps. So if you had a whole bunch of steps here, you could take the steps and you could get down there very safely. And you could add up each of the little gravitational potential energies for each of the steps, and that would get you down to the lower level. Or if you were, you know, a daredevil, you could like just jump right off. You know, probably break your legs, who knows. Wouldn't be very, very wise. But again, the energy that you would transfer to your body would still be the same as all of those little steps. You know, you could even, you know, we could make this silly, which I tend to do things like that. You could imagine that there's also an option to take a roller coaster, right? It doesn't really make any difference. You know, you could get on a roller coaster. You want me to put the car on the roller coaster too? Man, Lauren's looking at me like she can't, she's having difficulty visualizing the roller coaster. Anyway. And again, your speed would increase and decrease, and you'd have all these changes in energy, but in the end, if it was perfectly frictionless in this case, you would still end up with that same amount of gravitational potential energy. And that's because we have what is called the conservation of energy. And so it doesn't matter how you get to that final location, it's the final location that determines the overall energy. When you continue on in science, they'll call something that is only dependent on your beginning and end position. Has nothing to do with how you get there, right? They call that type of a thing a state function. And I always was confused by that. It really caused me a lot of pain, even after university. Why was that called a state function? And I was always thinking of changes of state and things like that. But they mean it's only dependent on its initial state, in this case, height 1 versus height 2. And the final state, it's only dependent on that. And it's not dependent on the path you take to get to the final state. All right? So something like gravitational potential energy is a state function. It just determines on how you know, from A to B, doesn't matter what path you take. Now, if we were to add friction into that, let's say you added friction, like air resistance and the roller coaster's wheels friction, then friction takes some of that energy away. It sucks it away. The longer the roller coaster you have, the more energy would be sucked away. As soon as you put friction into it, it's not a state function anymore, because it depends on the path you took to get there, all right? So if we had an ideal situation here, it's a state function. Chemical reactions, because heat at a microscopic level doesn't just disappear, right? You've got to have a conservation of energy. It's a state function. So if you're starting with reactants and you're ending up at products, it doesn't matter whether you do it in one shot, one chemical reaction, or you do it in 1, 2, 3, 4 different simpler chemical reactions. As long as it ends up in the same products, it's going to be the same amount of energy. You just add up the steps. And that's because energy is a state function. It has to do with that. Okay, let's do some examples. So hopefully that gets across to you why we can do this, and it's all about the conservation of energy. And now the last part of the lesson here is essentially how to do this. And I truly only have 2 examples to do here. I'm going to be done this lesson again quite quickly. You're getting a lot of time these days to finish work and I'm also letting you have it because, again, I'm allowing you to ask me questions about stuff that I was away for. Hopefully we can get that stuff cleared up. So when we start manipulating our questions in order to solve the problem, sometimes we need to flip a chemical equation around. Sometimes we need to make the reactants products and the products reactants. In other words, just a little left-right flip. When you reverse an equation, you're essentially Yeah, making reactants, products, reactants, which essentially turns an endothermic into an exothermic, or an exothermic into an endothermic. You flip what the reaction becomes. And therefore, when you flip the reaction, you also change the sign of the delta H. And I do that step very algebraically, all right? I simply say if I want to flip it, I'm going to multiply the entire reaction by -1. A flip and change the sign on the delta H. Very simple. Sometimes I need to multiply a reaction by a factor. Sometimes I need to double it. I could multiply it by a half, but that gets into, fractional coefficients. If we can avoid fractional coefficients, it makes life a little easier. But if you change the reaction, if you double the reaction, you've got to double your delta H as well, because you've made it twice as big, right? You've multiplied everything by 2. All right, those are the rules. Then when you're done and you get what you want, you add it all up and you've got it. You've got the answer. So like I said, a couple of examples, and then I'll let you, again, work for a fair bit. All right. Now, unfortunately, when you do a question like this, you are supplied with a series of reactions. You can see there reaction 1 and reaction 2. And when doing practice problems or examples, you have to copy them all out. It's a pain. But when you do them out of the textbook, you don't have to rewrite it. So they're not going to be as much writing as it is when we do the examples. Same with on a test. I give you the question. You go ahead and manipulate from there. You don't have to, like I said, you don't have to rewrite again. Now, ideally, I'd like to do this on a smartboard so we can record it all, but I should have left myself a little more room. You guys have more room underneath there. I'll see if I can squeeze it in there. I'll do the writing here, and then I might have to switch to the notebook screen so that I've got more room to write. But you guys will have all the stuff in front of you. Now, I very often start with a harder example, because I want you guys to get an impression that sometimes it is a difficult question. But this is only harder because I haven't given you what the final reaction is that I want to solve for. That final reaction is the enthalpy change for the formation of 2 moles of NO2 from its elements given the following equation. So in this particular example, we have to come up with what the final equation is that I'm going to get when I manipulate these two. The easier version of the question, I just give you what that final equation is, and you just go ahead and manipulate it. So let's first come up with that equation. I want an equation for the enthalpy change for the formation of 2 moles of NO2 from its elements, and that's what my reaction has to be. So I want to form 2 moles of NO, not NO2, but 2 moles of NO. So what am I going to pick here? Oh yeah, I got that as yellow. So my final reaction has to have 2NO, that's what I want to form. And it's going to be from its elements. So what are the reactants here? Yeah, what do you got? Yeah, and it's N2 and O2, right? N2 plus O2. And in these particular reactions and questions, these particular questions, state becomes very important because we could be just talking about turning a liquid into a gas. So we do need states here, and this is obviously a gas. We know that nitrogen is in the gaseous state. This is a gas as well. Oxygen is a gas as well. And NO is nitrogen monoxide. It's also a gas. Again, I would tell you that type of last bit of information there. I don't expect you to know all this stuff, but nitrogen oxides are gases. Okay. So this is what I want as my final reaction, and ultimately I want to figure out its delta H. So that's what the question is asking. And I've been given these two reactions. And I will give you reactions such that they can be added up in some way to get that reaction. That's exactly what we have to do. We now have to manipulate reaction 1 and reaction 2 by either flipping it or multiplying it by a factor such that we can cancel things out when we add them that results in this reaction. The tactic that I use, this is the way I do this, and it works quite well. I look for my reactants and my products in the reactions that I'm given. I see here that I have 2NO as a product. And if I look for NO, it only appears in reaction number 2 as a reactant. But in the end, I have to have it as a product. So what that tells me is, in order for me to add these up such that I get NO as a product, I must flip this reaction over at some point in time. Because when I start to add things up, I need NO as a product. It doesn't matter which chemicals you start with in this tactic. I just picked out the NO because I know I need that as a product. I could have worked with N or O2, but I'm noticing that I've got O2 in both reactants. Sorry, see what I mean? In both reactions here, which means I don't know whether to flip or how am I going to make an O2 out of a half of an O2 and an O. That becomes confusing. There's only one NO. I know I've got to flip that thing. I also need 2 NOs. So not only do I have to flip it, but what else do I have to do with this reaction in order to get my 2 NOs? I have to multiply it by 2. So what I'm going to do with this thing is, and this is the way I do this, I'm getting now my plan, I have to multiply this guy by -2. Because negative is a flip, and 2 doubles everything. So I came up with my -2. Let me put a circle around that. I like to put circles around it. I don't know why. I came up with my -2 by looking at my overall reaction, seeing that I needed NO as a product, and I needed 2. I got to multiply that thing by -2. All right? Again, looking at O's seems to be confusing. I'm not sure what to do with the O's because I got O's in both of them. But looking at N, there's only N in one reaction. So I can firmly, determine what I need to do there. In this reaction, it has 0.5 N2. I need 1 N2. I don't need to flip it. No need for the negative. But what do I have to do to the top reaction? Yep. I have to double it. Times 2. All right. I now have my plan. Now I'm going to actually do that. Now I don't have enough room on my screen, and so therefore I'm going to change to the smartboard one, to this one. I'm going to get a new slide. Let's get a new slide here. And I need you guys to tell me, what were the reactants on that first one? I'm just multiplying it by 2. So if I double everything, I'm going to have 1, 2, and 2, right? Correct? If I double everything? If someone could tell me what to write there, that would be great. I have what? 1 and 2, right? And 2 plus, and that's gas. What's the next one? It's going to be when I double that. 2O2. 2 O2, gas. And what's the final product of that thing if it's doubled? 2NO2? 2NO2. Excellent. Delta H equals. Now, at this point, you could also multiply the delta H by 2 and actually write it down that way. But what I like to do is just put a little times 2 behind it. So what is the delta H for that reaction that we first said? Positive 34? So what I like to do is put plus 34 and then just put times 2. Because that's what I did to this, so that's what I have to do to that. Make sense? Could somebody tell me now the flip and then multiplied by 2? And I suggest one thing. When you do your writing, put your arrows right above and below each other, because if you don't have your arrows lining up, you sometimes mistake a reactant for a product if they don't line right up. So I would like someone, hopefully, to tell me what the flip is, right? So what's my first reactant on that one after a flip and a double? I need a flip and a double. What's my reactant? Yeah, Christian? Yeah, 2NO2. And that's the only reactant, right? 2NO2. So we'll put it close here. And it's a gas as well, right? We're dealing with all gases. Keep going, Christian. For the flip, and now I need the other guys. An O2 gas and 2, sorry? 2NO and the delta H. Just tell me what the delta H was before the flip. That was before the flip? Negative 56, and what I do is I put a negative 2 behind it. Now, if you really wanted to actually multiply that by negative 2, you could put that number in there too if you'd like. Now, what do we do? Just like algebra. Remember when you did the good 3 unknowns and you're solving, you're multiplying x's and y's and z's, and do you still do that in math? Don't you do that anymore? Solving linear systems? It doesn't matter. What I now do is I cancel out anything that is a reactant in one reaction and a product in the other reaction, because they're literally not part of this final reaction. 2NO2, 2NO2. Gone. I've got 1 O2 as a product on this one, and 2 O2 there, gone, and that guy's turned into a 1. Yeah, it gets messy. I like these problems messy. I've canceled out everything that I can possibly cancel out. Now, without looking back, so I'm not cheating, I'm going to write down what's left. Reactants, I've got an N2 gas. I've got an O2 gas. Those are all the reactants. Products are gone. I've got 2NO gas. Did I successfully manipulate my equations to come up with the equation that we wanted? Yes. Therefore, the delta H for this reaction will be the addition of these two things. Now you just run it through your calculator. 34 times 2 plus negative 56 times negative 2. Or if you wanted, you could cancel those negatives out, however you wanted to do that. And you'll get a delta H. And that will be the delta H for that particular reaction. And I'll take that number when you get it. What do you got? 180? Yeah, 180? 180 kilojoules. And this isn't a molar enthalpy. This is the enthalpy for this entire reaction, which means it's how much energy we get per 1 molecule of N2 and 1 molecule of O2 and 2 molecules of NO. Pretty straightforward business. Okay, let's do one more example. So again, a lot of writing. But when you start doing the practice problems, they're right there in front of you in the textbook. Or I'm going to show you a website where you can find all kinds of these different things, however many you want to do. But unfortunately, you got to write out all this stuff the first time around. Notice in this one, it's asking for 10 kilograms. Well, that means we just have an add-on question at the end to convert our kilojoules for the reaction into kilojoules for 10 kilograms of the reaction. So there's just a little add-on kind of calculation. First, though, we've got to figure out what the energy is for just this reaction itself. We'll worry about the 10 kilograms when we get that Hess's Law problem done. So this one's a little easier. I've already given you what I want as the final reaction. Again, the states become very important. I don't know how far you are in the writing, but if you've made it to the third reaction, you'll notice I've given the simple reaction of converting H2O gas to H2O liquid, which means we may have to deal with that. It's not a problem. So again, my tactic is pick a reactant or product in the overall reaction that only appears once in our subsequent reaction and manipulate the reaction in such a way that you put it in its proper place with the proper coefficient. If you pick a reactant or product that appears in more than one, you don't know how to manipulate it. There's no easy way to see the manipulation. So simply go through your reactants and products of your overall reaction, find ones that appear only once, and manipulate the reaction so that it puts it in the right spot with the right coefficient. If you can do that with all three, everything else will work out. Everything else will cancel out and it'll become right in the types of problems that we give you. It just works out. So which one would you like to attack first? Has anybody spotted? Yeah, what do you got? You want to look at this reaction? And which chemical are you looking at? Which one are you? You're looking at the HCl because it doesn't appear anywhere else. I agree. What would you like to do with this reaction? I agree. -2. We need to flip and we need to double it. -2. It's that easy. -2 multiplication factor times whatever. I put times -2, -2 times. You get the idea. Perfect. -2. And that's the only place it appears, so it's got to be correct. We're not giving you reactions that don't work out, right? We're not trying to mess you up. Does anybody see another reactant or product that we could manipulate so that we could get it into the right spot? Christian? It's only one in here? Okay, what do I have to do with this reaction? So I need to double it, and then I've got it in the right spot with the right coefficient. I agree. ×2. 2 times. Now we haven't manipulated the what do you want to do? You're right. Gas. We're looking at the gas. So what do I have to do with this guy? -2, because I need the gas on the right side and I need it doubled up. So I need a -2 times. Well, we've done all that we really can do, and now we hope that everything works out in the end. And from what I've noticed, doing many of these problems, it always does. If you pick the ones that only appear once and make it into the right spot with the right multiplication, you're good. So now you're doing a rewrite. You're going to literally flip, put your -2 on the back end, double everything up, put a ×2, flip, -2 on the end, check that you got the right one, add it up, and you've got it. And I'm not going to do that one on the board. You guys can handle that at this point, can we? Handle the flip? All that stuff? I'll take your final delta H in the end. Again, it's easiest if you line up all of your arrows once you start flipping. I've seen students make mistakes. Okay, who's kidding who? I used to make mistakes such that if I left it written like this, I would look at that liquid and do something stupid like cancel it out, even though they're both on the right side of the arrow. It's because the arrows didn't line up. You line up all those arrows, you'll always be canceling out the right ones. Get those arrows to line up. Right, so after the flip, on the left for your first one, you should have 4 HCl, aqueous. Then for products on that first one, 2 H2 gas, 2 Cl2 gas. Maybe I will do a quick little write down just to... These are all in kilojoules. And what do we do with the last one? A flip. So 2 H2O liquid, 2 H2O gas. Oh, and we double the flip and a double. Negative 4, 0.7, negative 2. And I forgot to multiply that guy by 2. The reason I wanted to run through it was, again, just to show you the canceling. 2 H2O liquid, 2 H2O liquid. My eyes are drawn to that one first for some reason. 2 H2 gas, 2 H2 gas. And that's it, right? I think I've canceled it all. Now if we write down all of our reactants, 4 HCl aqueous, O2 gas, that's taking care of all of those. 2 Cl2 gas plus 2 H2O gas. That's what we wanted. Add up all those things. So you get, again, however you calculate it, don't get locked into putting these numbers in your calculator. A quicker move to save you seconds on a test. Those negatives cancel out, right? So 185 times 2 plus negative 285 times 2 plus, those cancel out, 40.7 times 2, right? Make things easier on yourself as you're putting them in. What do we have for a number? Somebody got a final number? Yep. 20.2 kilojoules. We got supporters on that, all right? So I'll write that in here. Negative 120.2 kilojoules. Now, unfortunately, the question isn't done yet, all right? We have to figure out how many kilojoules that we would get with 10 kilograms of HCl. And this goes along with some of the questions that you're doing in your calorimetry as well. If I have 10.0 kilograms of HCl, I need to convert that eventually into kilojoules, because that's what the question asks. What's the enthalpy change? So I need a conversion factor or an equation that's going to get me from kilograms to, well, what can I turn that kilograms into? Even if we don't know where we're heading, what am I going to turn that kilograms into? Yep, moles. And then I need to get from moles of HCl to kilojoules. And that last step is all encompassed in that overall reaction. What would you like to do? Somebody guide me here. am I going to get from kilograms ultimately over there to kilojoules? And this is the chemistry IQ that we need here. We need to take those little steps that we know how to do to get us along the way. Suggestion. Even if it's a little starting suggestion, a tiny little suggestion. Yep. Yeah, let's turn it into grams. Easiest way to turn kilograms into grams. What do I put on the end? Times 10 to the 3. HCl. Next little baby step. Yep. Change it into moles. Have you figured out the molar mass? 36.5 moles, grams per 1 mole. Now, we could get moles and then do our next thinking step, but in actual fact, I can create a conversion factor that will relate moles of HCl straight to kilojoules. I just have to create it out of the chemical reaction. Tell me a true statement about moles of HCl and kilojoules that come from that particular chemical reaction. I just need a true statement on how moles relates to HCl in that chemical reaction. You don't need to put it as a conversion factor. What's true about moles of HCl and kilojoules in that reaction? Yep. Exactly. For every 4 moles of HCl, you're going to get negative 120.2 kilojoules given off. So if I've got moles on the top here, I've already gotten rid of my grams. What am I putting where in my conversion factor from that statement? Yep. Yep. For every 4 moles of HCl, you get negative 120.2 kilojoules. That's going to get you the answer. We just pulled it right out of the thing. What that actually is 2 conversion factors in one. It's our mole ratio and our molar enthalpy all squeezed into one conversion factor. But there's no need to separate it into 2. It's a true statement about the reaction. That's going to do it. It's going to take care of everything. You could have figured out the moles. You could have figured out a molar enthalpy by taking this number and dividing it by 4, getting a molar enthalpy, then putting it in the equation for molar enthalpy, and eventually get the enthalpy. Same problem, just a different path. To me, this is the easiest path. What do we have for energy? 10 kilograms. How much energy do we get? Yep. Kilojoules, what are we dealing with? 3 significant digits, negative 8230 kilojoules for 10 kilograms of that reactant. Okay? Which would, which again is the difference between a delta H. That's how much energy we got of 10 kilograms. And then this is, it's not a molar one yet, but we could make it a molar one where it's just telling us for this reaction. Okay, so there is Hess's law. This chunk here in the middle that we added up is Hess's law. That's just doing some extra problems dealing with it on the end. Okay, so homework problems out of the book, right there. And again, this note is online. And I've got a little link here. I hope it still works. There is the website. It's been around for a long time. Many university courses have all kinds of different interactive, ways of practicing problems, etc., etc. This one is really good. I'm just going to show it to you. It's very simple. It's not flashy. You can see that there's not, there's a regular type there, and it doesn't have a whole lot of, bells and whistles. But right here has all of the different kind of topics that we cover in chemistry. And you can see here there's a thermal chemistry. If you click on it, it'll make you jump down to the thermal chemistry spot. But I'm just going to go over some significant digits, exponents, scientific notation, even some dimensional analysis for volume, mass, distance, and densities. If you wanted to practice your good old protons, neutrons, and atomic notation, all of this stuff is in here. Boyle's law problems, Charles' law problems, combined gas law problems. So I'm going to jump down here to thermal chemistry, and here you can see Hess's law, and I'll click on the star. And what happens is it gives you a little scorecard. Let me get this little thing out of the way. That's for my smartboard. And if you click New Problem, a new box comes up, and it essentially gives you the final reaction, the two reactions. Flip them around, get the overall, put your number in. It'll keep score for you. It's just a very simple website, and it's got all kinds of different practice problems. Like I said, if you wanted to, you could practice some of your combined gas law or let's do ideal gas law problems. And if you get a new question, it'll simply, here it is up top, what would the pressure in torr be if an ideal gas has that many moles, occupies a volume of that many milliliters, and the temperature is negative 113 degrees Celsius? Calculate away, stick in an answer. It's not flashy, but it'll just generate problems for you if you want to do a few extra problems. It's a neat site in that it's very simple and has all kinds of stuff on it. Okay, so that's just a little extra there. Any questions or concerns? All right, work away.